Hello everyone, welcome to A plus BI. In this video, well, first of all, this channel is all about complex numbers. And in this video, we're going to be solving an exponential equation with complex numbers. So we had 1 plus I to the power n equals 256, and we're going to be solving for n values where n is an integer. Or does it have to be an integer? That's a good question, right? So let's go ahead and find out. And there's definitely more than one way to approach this problem. Let's go ahead and start with the first approach. So, to be able to solve this problem, I definitely want to write 1 plus I in polar form. Thanks to Euler, we can write a complex number in polar form. You just need to consider how this number is displayed in the plane, which we call Argand plane, by the way. This is imaginary, this is real, so on and so forth. Obviously, this number makes an angle. You can think of this as a point or a vector, and obviously it makes an angle when you draw that as a vector. Now, how do you find that angle? Looking at the coordinates, using a little bit of trigonometry, you notice that theta is equal to pi over 4, and r is considered the absolute value, and r is the distance from 0. Basically, that will be square root of 2 from the Pythagorean theorem. So that's the two pieces of information you need. And in that case, our number z can be written as r times e to the power I theta. Again, thanks to Euler, we have this form because e to the I theta can be written as cosine theta plus I sine theta. And guess what that brings us? That brings us the most beautiful equation in mathematics. Great, now let's go ahead and see how we can use this information. So our number 1 plus I, which is our z in this case, can be written as square root of 2 multiplied by e to the power I times pi over 4. Obviously, we're allowed to add multiples of 2 pi to this, so you can also write this as pi over 4 plus 2 pi n, where n is an integer, okay? Now, that represents the rotations, but since we're going to be taking powers of 1 plus I, and n is an integer, by the way, I shouldn't use the same n here, I guess, maybe something like k, right? Basically, we don't really need that 2 pi k. Why? We only need it for roots, because that's when the angles or arguments get smaller, right? So let's go ahead and, just forget about the 2 pi k. You can just take k equals 0 in this case. So our number becomes root 2 times e to the power I times pi over 4. So that's 1 plus I. And guess what we're going to do? We're going to raise it to the power n. And what happens when we do? Let's go ahead and take a look at it. If I raise something like this to the power n, obviously, two things happen. We have a product. Root 2 is raised to the nth power. And e to the power I pi over 4 is raised to the nth power. And at the end, they're supposed to give us 256. But wait a minute. Can we not write the 256 in polar form too? Yes, we can, considering the fact that it is a real number. 256 is going to be appearing on the real axis on the positive side. So it's going to be, obviously not drawn to scale, but it's going to be something like this. The distance from 0 will be 256. In other words, we can write this as 256 multiplied by e to the power I times 0, right? Wait a minute. In this case, you need to add the 2 pi, because guess what you're going to do? You're going to need to divide in this case. So we're going to write it as e to the power I times 2 pi k. Okay? Now, what happens if k is 0? We get 256. If k is 1, we get e to the power I times 2 pi, which is, again, 1. So it's kind of like the complexified version of 1. But now, if we put these two things together, your equation is going to make much more sense. Let's go ahead and do that. Root 2 multiplied by e to the power I pi over 4 to the power n equals 256 multiplied by e to the power I times 2 pi k. Again, k is an integer just like n. Okay? Now, where do we go from here? Well, here's the thing. First of all, on the left-hand side, we have to distribute the exponent, the n. So it's going to be like square root of 2 to the power n multiplied by e to the power 1. Now, when you multiply I times n times pi over 4, that's going to equal 256 multiplied by e to the power I times 2 pi k. Awesome. Now, at this point, you can definitely compare the, the modulus or moduli and the arguments. because the only way these two things can be equal is when these two things are equal and those two things are equal. Obviously, you can also find out by dividing both sides by e to the I2 pi k, so that you can put the powers of e on one side and everything else on the other side as a power of 2, and then you can also go from there. But I think this comparison will be a lot easier. Okay, great. Now let's go ahead and take a look at this first. Square root of 2 to the power n equals 256. How do you solve an equation like this? I know you're probably saying something like, hey, I'm going to use logarithm. Yes, you can, but you don't really need to. Think about this. This is 2 to the power 1/2. To the power n, it's just going to be 2 to the power 1/2 of n. And as you should know, 256 is 2 to the power 8. So what do you get from here, right? Well, if the bases are equal, so are the exponents. So half of n is 8, which means n is equal to 16. Wait a minute. Do we have to solve for k? Well, no, we don't have to. But let's just take a look, okay? Because our goal, remember, was to solve for n, right? Not for k or anything. K is something that we kind of introduced. But let's still compare these two things. Since we know the value of en right now, we're going to get e to the power I n pi over 4 equals e to the power I times 2 pi k. Now, if n is equal to 16, this is going to give you e to the power 4i pi, and that's going to equal e to the power I times 2 pi k. And from here, definitely, you're going to be getting something like 4i pi equals 2 pi ik. If you do simplify this a little bit, you can cancel out the I, you can cancel out the pi, you can divide both sides by 2, and guess what k gives you? K gives you 2. Now, what happens if k is equal to 2? Then you get something like e to the power 4 pi. E to the power I times 4 pi. Is that meaningful? I don't think so. Because we already got the n value, I don't think it's going to contribute to anything. But let's go ahead and take a look at the second method real quick, because I think that's also pretty interesting. Now, one thing that you should definitely know is there are two special numbers whose powers are super special. And one of these numbers is 1 plus I, the other one is 1 minus I. Why are they important? Because if you take 1 plus I and raise it to the second power, you get 1 plus I squared plus 2i. I squared is -1, so they're going to cancel out, and this gives you 2i. And if you take 1 minus I to the second power, you get 1 plus I squared minus 2i. I squared is -1 again. Oopsies, I forgot to say that at the beginning, but I already said it now. That's -2i. So why is this important? Because look at this. 256 is an integer. Powers of I can be turned into integers, and I have the same base. So the idea is then, okay, fine, 1 plus I to the second power is 2i. Can I raise it to higher powers? For example, what happens if I square both sides? I get fourth power, and that'll be 4i squared, which is -4. Wait a minute, I can go from -4 to 256. Let's square both sides one more time. That gives us 16. And as you should know, 16 squared is equal to 256. Therefore, in this case, n equals 16 works. But the million-dollar question, again, is n equals 16 the only answer? Suppose n doesn't have to be an integer. Can we find other solutions? That's for you to find out. Because this brings us to the end of this video. Thanks for watching. I hope you enjoyed this. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe. Take care. Don't forget to check out Cybermath and the Shorts channel. And bye-bye.